So today we are going to see another example of greedy technique, and I'll take an example of one of the most important famous problem of encoding or data compression you can think of. Right? Uh, it's known as this Hoffman encoding. So first, I'd like to give you the problem statement as usual. Right? So what is the problem? So suppose we have a Word file. Let's say uh, we have some data file, some kind of document, and it's a and this document is over some alphabet. So I'll say this sigma. Right? What do I mean by this? So if I only think about just my document is some kind of English paragraph. Right? So then what is the alphabet set for this paragraph? It's the letters, all the letters in both capital and small cases, and all the punctuation marks, right? Like comma, full stop, semicolons, and all. Right? Is there a problem with my voice? Am I audible clearly? Okay. 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 So for English paragraph, that's the alphabet, right? So think for an example. Let's say I have a document that consists of just four A, B, C, D, and my document is a sequence of these four letters, maybe C, A, B, D, something like this, right? Uh, Maybe if you're not able to hear properly, maybe it's a problem from your end. Everyone else, I think, can hear properly. Okay. Fine. So this is the document that we have, and this file is over some alphabet, right? And in this example, I have taken this ABCD, right? Now, when we store this document in our system, it's basically we know that it has to be converted into binaries, right? So everything we store in our systems in binary number system, right? So what we do, we uh, we convert, we can convert mm, each of these letters with some binary representation. Maybe I can say that A is something like 0, 0. Then B is something like 0, 1. C is something 1, 0. D is something 1, 1. Right? And then based on this encoding, I'll convert this document into some strings of zeros and ones. Right? That's the uh, encoding of this document. Right? So we call it a fixed length binary encoding. Usually, I think you have seen an example of this. While coding, you must have seen the ASCII codes of the all the symbols that you have, characters, right? So for each of these characters, we have a binary sequence of length 6, right? Those are same thing. Like in this case, I'm fixing the length to be 2, right? Okay. So now it might. This is well and good, right? Now suppose that in our document we see that see in this case so why you are calling it fixed length, because all these characters length of the encoding is fixed for every character, and which is 2 in this case. Okay, so what would be the size of this document? Size of this document means the total length of these documents. It will be the number of letters that we have in the document times 2. Right? That will be the size of the document. Right? Now, our goal is to improve the size of the document. What do we mean by improving the size of the document? So, it's document we generally store in our system, right? The lesser the size of the document, it will be better for us, right? Because we all like to do this compression, data compression, right? So we don't want to lose any information about the document, but we want to store them in such a way that it takes lesser amount of memory. Okay. So the question is, can I do that? For that, we can achieve actually. So let's say I tell you that the okay, let me tell you something like this. So in my document, the frequency of all the letters are different. Frequency means the number of times those letters are appearing. Okay, so let's say A is appearing uh, A is appearing 0.6 time. That's 60% of time A is appearing. B is appearing, let's say 25%. 10% I have C, and let's say I have how much? So 7.05%. Right. This is the 5% I have D. Okay. These are the frequencies of these letters in my document. Right. So earlier what we had, what was the average length? So in this case, when we have fixed length binary encoding, what was the average length of these of this encoding? Average encoding length, what was that? It's 2. Since it's fixed, for every character, every symbol, I have used a binary encoding of length 2. So its average encoding length will also be 2. Okay. Now suppose that in this case, when I know that frequencies are of this form, then which one would be easier. Right? So if I somehow able to encode the higher frequency values with encoding length less number of bits in it, then the size will be small, right? So for example, if I say that I would like to encode A by 0 and B by 0 1, C by 1 0, and D by just 1. Right? This is, suppose this is the encoding we are considering. Right? This we call, now the encoding length of each of these characters are not fixed. Right? We call it variable length binary encoding. Length of each of these letters are different. Right? Now, in that case, can you tell me what would be the average encoding length? So, 60% of the time I have used an encoding of length 0, right? So, what would be the average encoding length? So, 60% of the time I have used, this is the frequency of A, right? And what's the length of A? It's 1. Plus 25% of the time, this is the frequency of B. These many times I have used an encoding of length 2. Another these many times I have used, another 10% of time I have again used an encoding of length 2, and lastly 5% of the time I have used an encoding of length 1. Yes, so this will give me the average encoding length. Okay. Can you tell me what it is? 0.5. This is 0.5. 1.35, right? Okay, is this clear? So see, it's better than the average encoding that we did last time. Average encoding length is reduced, so that says the size of the total size of the document will be smaller, right? So I am able to compress that. Can you explain average encoding length again? Average encoding length is like the frequency of, it's the frequency of each of these characters. That's these are the frequencies. Point 1 is the frequency of 1. Frequency means the number of times those letters are appearing in my document. Right? It's a frequency times the length of the encoding. Length of A is 1. Why? Because this only 0. Right? Length of B is 2. Length of C is again 2. Length of D is 1. Is it clear now? Okay. So I'm able to compress my data. Okay, fine. And now see, okay, so far we have gained something in terms of data compression, but there is a problem. Right? The problem is kind of ambiguity. Right? So I encode the data is fine. That's okay. Right? I'm able to compress the data even. Right? But while decoding, so I actually, and later on I might need that document, right? That's why I'm storing it. Suppose I see that uh, there is one portion of uh, the data says encoded data says 001. Then can you tell me what that original letters were? It's AB, right? So it's okay. So this is your A, this part is B. Okay, fine. But is it the only decoding? So this is the decoding portion. I can think about the same thing as this is A, this is A, and the next thing is a D. Yes. So that's why I'm saying there's an ambiguity. Right? What's this ambiguity? That same code is having different interpretations. After decoding, I can get two different things, right? So I don't want that. We like this type of ambiguity, right? So then what is the way out? See, what is the problem here? Problem here is this B. If you think this encoding of B and encoding of A, and similarly encoding of C and encoding of D, like similar situation will occur if we have, let's say, 110, right? So someone can say that this is D and then C, or someone can say this is D, D and A, right? Again, many such conflicts may appear. Right? Now, why these type of conflicts are arriving is because if you just focus on this B and A, this B itself, I can write it as, sorry, this is 0 and this is 1, right? This B itself, I can write it as A D. Right. So the encoding, the problem is appearing because the encoding of A is appearing before the encode. So in the encoding of B contains encoding of A. The starting portion of, like, the first part of this encoding is same as the encoding of A. Right? Similar thing is happening for C and D. The encoding of D is appearing at the beginning of the encoding of C. That's why this problem is arising. So there's a problem of treating this value separately. Okay. So if uh, wait a second. So that's the problem. Right? So what do I want? So the, uh, yeah. So okay. So in general, so I can set up some different encoding, but that will work fine. But I want to. Uh, I just pointed out why these type of problem is appearing. Right? So the encoding. Let me write it as well. The encoding of uh, A is appearing as prefix in the encoding of B. Right? Encoding, sorry, this one. Encoding of A is appearing as a prefix in the encoding of B. That's the problem. So to overcome this, what do I want? I don't want such prefix of this. What I want is kind of we call this as let me highlight this. This is a fixed length encoding. Then from this, I go to variable length encoding. I I need variable length encoding because I want to compress the data. But while compressing, we have seen that we have run into ambiguity, and this ambiguity is appearing because of this prefix. Right. So what do I want? I want prefix free variable length encoding. Okay, so my job is to give you an encoding of variable length, and also it should be prefix free. Okay. What happens if I set this A to 0, B to 10, C to let's say 110, and D to 111? Okay, suppose this is happening. Again, so think about the frequencies. Frequency is 0.6. This is having 0.25. This one is having, C is having 0.1, and D is having 0.05. Right? Okay. So in this setting, let's say, I'm not saying this is the only prefix free encoding. So I've just taken an example of this. Again, it's a variable length because some of the lengths are 1, 2, and 3 as well. Right? So do you think the average encoding length may exceed 2? So I've seen this fixed length encoding. In the fixed length encoding, average encoding length was 2. But in this setting, if I encode the symbols in this way, and this is the frequencies that I have, do you think the average encoding length may exceed 2? Is it possible to have average encoding length more than 2? It's most likely not, because uh, this length is 3, this length is 3, right? But 3 length encodings are appearing very less number of times. Only 15% of the time we are using an encoding of length 3. 25% of the time we are using an encoding of length 2, and most of the time we are using an encoding of length 1, right? So can you tell me what would be the average encoding length in this case? Okay, you just calculate this. I'll just take a short break. I'll come. Okay. Yes. Hello, can you hear me? Am I audible? Okay, fine. Uh, yes. So the average encoding length is coming out to be 1.55. Right? So we are gaining in terms of average encoding length because we are able to compress the data, right? And also now if you see that none of the encoding is appearing as prefix in any other encoding, right? So that's the so what is the problem statement? Let me write the problem statement to you. So what's the input? I'll be given the document, right? And I can think of that. So I started with the document, right? And in the document is actually we calculated the frequencies of each of these letters, right? So for simplicity, I will assume that the input is that in the document, what is happening that's given. I don't have the document, but I have all the relevant informations about the document. By relevant information, I mean that I know what are the letters used in it. That is, I know what's the alphabet and I know what's the frequencies of those symbols from the alphabet. Right? Okay. So the input is a non-zero value, no, sorry, non-negative frequencies. I'll say PA for each symbols A in the alphabet. Okay. And I can say that the in the alphabet there is at least two symbols, right? So more than one symbols, right? And what is the output? I want a prefix-free variable length. I can omit this variable length. I just say prefix-free binary encoding. Yes. Uh, prefix free binary encoding of the symbols of alpha, right? So this is one. This is an example. But is it an optimizing problem? I can give many different prefix-free encodings. Yes. But what is our main objective? I want to compress my data as small as possible, as like the size of the data. I want to make it very small, right? So I want to basically reduce this average encoding length as small as possible. Okay. So my ultimate goal is to give you a prefix-free binary encoding of the symbols of the alphabet with minimum average encoding length. Okay. Right. So what's the average encoding definition of this average encoding? It's in this term, right? So it's like, as I said, it's a frequency times the number of bits used to encode A, right? And I have to, so it's a frequency of A and the number of bits used to encode A, and I should be adding this quantity for all the values of A. For all the symbols, I have to get this. Okay, is this fine? Any questions so far? Okay. Okay. So now I will, before going into how to solve this problem, I'd like to give you another way of looking at this solution. So looking at this encoding, I'll give you uh, how to present this encoding, representation of this encoding. One way of that I'm using is like, what is the encoding of A, what is the encoding of B. I'm specifically writing what are the encodings of A, B. Right? Actually, there is a smarter way of representing the encoding of the encoding of the symbols, right? And that smarter way is by using a tree-like structure, a binary tree. Okay. So let me just draw the connection between trees and these codes that you have, right? Uh, okay, so for this example, let's say when we had this fixed length binary encoding, right? This one. I I can represent this by a tree-like structure in the following way. Let's say I this is the node. Here I have another node. Then I have two other nodes. I have A, B, C, and D. Okay. What am I doing? I'm drawing a binary tree, and I'm putting the symbols as a leaf node of this tree, right? And along the branches, along these edges, I'll put some value, and the binary value I'll put. The left branch, I'll put 0 for every node. For every internal node, in the left branch, I'll put 0. In the right branch, I'll put 1, like this. Right? Now I'll see from the root, this is the root. From the root, while reaching the node A, what are the things that I am encountering? From this root, this is the way I can reach A. And what are the things that I'm encountering? 0, 1. Okay, so that's why its encoding is 0. For B, it's 0, 1. So, sorry, for A, it's 0, 0, right? 0, 0. For B, it's 0, 1. For C, it will be 1, 0. And for D, it's 1 and then 1. Okay, you got? Is this okay? This representation? Okay. Now, this is an example where we have some kind of ambiguity, right? So let's understand what is happening in here. Why do I have ambiguity in here? If I try to draw the tree representation of this encoding, then I'll realize what is the problem. So it is 0, A is 0, this is 0, 1. So that means so from the root, I have two branches, this and this. This is 0, this is 1, right? What this node would be? This node would be A, right? And this one would be D, okay? And from A, what do I have? 0, B is 0, 1, right? So B should appear as the right part of it. Since I'm always maintaining this thing, like when we have a node, if it's the left branch, then I'll put a 0. If it's the right branch, I'm putting a 1. So this is my B, and let me just redraw it. This is B, and this one is C. Right? So again, the same thing. How can I reach A from the root? This is how we reach A. And what are the things we encountered along the way? It's 0. So its encoding is A is 0. And what's the encoding of B? This 0 and then 1. Okay, this. What's the encoding of D? It's only this. Encoding of C, 0 and 1. Sorry, 1 and 0. Right, like this. Okay, got it? Any question? Yes, do you have any question about this representing a codes using this tree, binary trees? Okay. Uh, so now let me ask you, can you guess the problem In terms of the tree, what is the reason behind the problem of ambiguity? So this is an encoding where we have a problem, right? This is the encoding where we have a problem, and this is an encoding there's no ambiguity in it, right? Can you see in this tree itself, can you point out the reason behind the ambiguity? Or how can I have a prefix? One encoding is appearing as a prefix in another encoding. How could it be possible? In terms of a tree, what would happen in the tree if one encoding is appearing as a prefix? Yes, any guesses? See, prefix means what? The first part of the encoding will be same. See, how do I get the encoding of B? I'm getting the encoding of B first by getting the encoding of A and then followed by the rest of the part. Yes. So one symbol is appearing before I reach the desired symbol. Right? That means that the encoding of this symbol will appear as a prefix in the encoding of this symbol. Right? So to overcome this, how is it possible? How is happening? Because these encode in this tree, A is not appearing as a leaf node, right? It is appearing as a internal node. The nodes that are appearing not appearing as a leaf node or appearing as an internal node, those encoding will appear as prefix. Encoding of those nodes will appear as prefix. Okay. And what can you say about the length of the encoding in this in terms of this tree? What can you say about the length of the encoding? What's the encoding length of this? 2, right? So the depth of the leaf, depth of the node. So from the root, what's the depth of this node? It's 1, just one level down. What's the depth of this node from the root? It's 2 level down, right? The encoding length is 2, like this. Can you give me the tree representation, binary tree representation of this encoding of this prefix-free encoding that we have in C? So this is the root, and this is the left branch, and this is the right branch. Right? So in the left branch, what do I have? So it's 0. This is 1. Right? What would be in this left part? What would be in the left branch? This will be A. Okay. What would be in here? Will there be any symbol in this part? No, because if there is any symbol, then its encoding would be 1. But I don't have any encoding of this one, right? So I don't have anything in here. So it will be just an internal node. Again, from this internal node, I'll go to this part, right? So this is 0, this is 1, right? What is this? What will be this 0? 0 is representing this B, right? And again here I'll also not have anything. It will be just internal node. This is 0, this is 1. And what is there? 0, 1, 1, 0, that is C, 1, 1, 1, that is T. This is the encoding free representation of that prefix-free encoding. See, whenever we have prefix-free encoding, the symbols will appear as a leaf. It's an if and only if condition. If the symbols are appearing as a leaf, then it's a prefix-free encoding. Okay, so I'll give a special name to it. I'll name it a sigma tree. Sigma tree because it's basically representing the encoding of the symbols from the alphabet. Is a binary tree. Okay, with leaves leveled in 1-to-1 correspondence with the symbols of this, right? Okay. Fine. Now, in terms of what is our ultimate goal, I'm trying to minimize the average encoding length. Right. Now, what would you like to, so length of an encoding, how do you get this length of an encoding? It's in terms of the tree, it's just the depth of that particular leaf. Right. So I want to construct depth. Yes. So to get the minimum encoding length, what do I have to do? I have to construct such a tree, such a binary tree, where the symbols will appear as a leaf, and at the same time, the average depth of a leaf, that will also be minimum. So we want such a tree uh, whose average depth of a leaf is minimum. Right? Is this clear? So encoding of a symbol is basically the depth of that particular leaf corresponding to that symbol, and I want to minimize that. Okay, so let me just use some notation for this. For a sigma tree T and symbol frequency set, let's say frequency set P is given PA, A belongs to the sigma, we denote LT P. So T is the tree and P is the frequency set, right? Of all the symbols is the average depth of a leaf in T. So how do I define this? This one is nothing but the same definition. Right? For all the symbols in the alphabet, frequency. Earlier, what we did, I multiplied this number of bits, and this time I'll say in terms of the tree, this will be the depth of the leaf. This will be the depth of the leaf labeled as A in the tree T. Yes, so far, is it good? Any questions? So now we will see how to get this one, right? So for this example, let me go back to this example. के बाद वो yes, this is the multiplication. This is just the multiplication. PA times this. Okay. Now let's think about some idea of how to get it. If you think about the tree, okay, uh, which of these symbols should appear at the very bottom level of the tree? So I have few symbols and I know their frequencies. Which of these symbols you want to put at the very bottom level? So bottom level means its depth will be high, right? And I, overall, I want to minimize this quantity, right? Which now my question is, which of these symbols you want to put at the very last level or bottom level? So suppose what would happen if these symbols, frequency of these symbols are quite high? Then what would be the average encoding length? So what did I said that whether this average encoding length for this particular encoding is going to increase or not? I justified that it's not likely that its frequency will get beyond 2. Right? It will be still be less than 2. Right? Why? Because just 15% of the time we're using encoding of length 3. And this length 3 means that these are appearing at the very depth. I mean, depth of these nodes will be high. I like to, since I want to minimize the average leaf depth, so I want to put the nodes with lesser frequency at the deepest level. Okay. Those nodes I'll be putting at the deepest level. Okay. So what would be my strategy then? That's a greedy strategy. So I want to overall minimize something. So I'd like to, my greedy criteria is that I like to push the nodes with with minimum with minimum total frequency whichever is having minimum frequency, those nodes I'll be putting at the very last level. Okay, and then I'll have another tree. So let me tell you the idea how we should move about, right? uh, with that particular example, I'll go. So I take this here, A, B, C, D. Right? What were the frequencies I had taken? 0.6, 0.25, and 0.25, zero point 0.1, and 0.05. Right? These were the frequencies. Okay. Now, what I'll do, I'll arrange. Okay, so at this point, no need to arrange. So I will initially I'll think of this as a collection of trees. Right. Each individual symbol is a tree. So trivially, I can think of this. This is just a small tree with having only one node. This is another tree. This is another tree. So initially, we have all the symbols appearing as a uh, individually appearing as a tree, collection of all those trees. Right now, I have to combine. I have to merge these trees together to get a single tree. Right now, which of these two trees I'm going to merge? At this point, I have to decide which one of these trees am I going to merge them together. As I just argued that I am going to merge the minimum frequencies, uh, the trees having minimum frequencies. I'd like to merge those two together. Okay. So in this example, so this is a frequency 0.1, this is a frequency of 0.05. I'm going to merge them. How am I going to merge these things? So I'll have a node, I'll have 0 here. Sorry, I'll have C here and D here. Okay. This is how we're going to merge them together. I'll take a new node and I'll put these two nodes as a lead, as children of that particular node. I have taken this new node. I have put these trees as a subtree of this. It's okay? Is it fine? Any question? Okay. So now what would be the frequency of this particular tree, CD together? Now earlier we had C appearing as a single tree. This one is appearing as a single tree. Now what I have done, I have merged them together into a single tree. I also have to mention what's the frequency of these two trees. So this one tree, this combined tree. What is the frequency of this? The frequency of this one would be just frequency of these two things together. Frequency of this one will be 0.15. Okay. And also I have other things as well. This one is having 0.7. Okay. right? So what do I do now? Still, I have a collection of trees. Right? Now again, I'll do the same thing. I am going to add. I at this point I have three trees with me, right? And I want to merge two of them together. Which two I'd like to merge? The last two, B and the tree having CD. Right? Why? Because this and this are the lowest two frequencies available at this point. Fine. Oh, this is 0.25, right? B is 0.25. Right. Okay. So when I merge, how the tree should look like? I'll take a new node. I'll put this one as C, D, and this one as okay. Again, I'm doing the same process. I'm taking a new node. I'm putting one tree as the left subtree, another tree as the right subtree. Okay. Now, what is the frequency of these things together? This will be 0.6. And I have A with me. This will be 0.6. Okay. And then another step would be like I have just two trees left with me. So I'll have A in here. I'll have this whole tree, sorry, the whole tree as the right subtree. Good. At the very end, the total frequency is 1. And frequency is 1 means like I have covered everything together. Yes. Any question? Okay. Uh, okay. So I'll take a break and I'll come just 1 minute. Yeah, that. Okay. So this is the process. Let me write the pseudocode then. Okay. Uh, I think. Okay. So what's there? So initially for each of these symbols, right? I'll consider a tree TA. What is this tree? Initially, this is what the situation was. Each symbol was appearing as a single tree, right? Let me name this TA. This is the tree containing one node A, right? And what's the frequency of this? So P PA. This is frequency of this tree was PA, right? So frequency of these trees was this. Now we have all these collections. All this collection. This is the collection of all the trees that we have. This is the collection that I mentioned. This collection I am naming it as a. Okay. Can you tell me initially in general? So okay, I didn't mention it here, but so this is like for each symbol A in this. And what's the size of this? This number of elements in that alphabet is n, right? Let's assume that there are n elements there. Right? So can you tell me initially how many trees we'll have? Initially, initially I'll be having n trees, right? Okay, and at the very end, I'm having uh, only one tree. Right? Can you tell me how many times do I have to do this merger of trees? How many times I'm going to merge these trees to get a single tree? Initially, I started with n trees and till I get the minimum depth. Uh, minimum, I think, saying minimum average depth, right? But minimum average depth is a consequence of the process that we are following. But while designing, I am not checking is, yes, it's actually n minus one times I have to do this merger to get a single tree, right? And the process is such that it will end up with a it will give me a minimum encode, minimum leaf depth, average minimum average leaf depth. Okay. Okay. So I'll say that what while uh, while this f contains at least two trees, let's say, then do something. What is in the case? This is the T1, let's say, the tree with minimum frequency in F. Let's say T2 is the tree with second minimum frequency in F, right? And then I'm going to merge them together, right? So let's say T3 is the merger of these two trees, right? Merge T1, T2, right? And what would be the frequency of this? This will be frequency of the T1 plus frequency of T2, right? That's what we did. Frequency of this tree is this plus this. Frequency of this particular tree is frequency of this plus frequency of this, right? Like this. That's what I'm writing. Frequency of the new tree T3 is the frequency of P1 plus frequency of P2. Right? And I have to update my collection as well. So what should I write? This collection, from this collection, now this T1, T2 are gone. In place of them, I have T3. Right? So this collection will be like T1, T2 are gone now. From this collection, I am removing them and I am adding T3 with this. Okay. And what should I return at the end of this process? So while I although have written this while in terms of while, but I could have written in terms of a for loop also. For I run from do these process for I runs from 1 to n minus 1. Okay. So what should I return? Return uh, the tree in F. So there is only one tree now. When I finish this process, there is only one tree. I'm going to return this. Okay. So can you tell me how much time do I need to implement this? Just to find the minimum encoding length, how much time would you require? Yes. Or think in this simple form. So uh, you don't have to think in terms of like the trees even, right? So you just think in terms of the uh, encoding lengths that you have or the depth of the tree. So what is the process? So the process is that you are kind of you have an array in some simple form. Let's say, let's take the same example. You have this array and you are merging these things A, B, C. Oh, sorry. I'll be writing the frequencies there 0.6, 0.25, 0.1 and 0.05. Right? That's for A, B, C, D. Right? Like this. So then what you do, you find the minimum and the second minimum. So, and then you merge them together. Okay. How much time would you take for doing this? So I suppose I want to find the minimum and second minimum in this array. How much time do I take? So finding a minimum in an array, how much time would it take to find a minimum element in an array? It's O of n, right? So you have to check all the values. And second minimum also you can do it in O of n. So to find this minimum, finding min and second min, so you must be spending O of n time. Right? And then once you have this minimum and second minimum, then what you are doing, you are just adding the frequency. Like in this one, what do you have? Then 0 0.6, 0.25, and then you have 0.15, right? Like this. This is blank. Okay. You're just adding them. So this part will take just a constant time. Okay? And then again, you take minimum of these two. Again, finding this, find in this one, finding min and second min. It will take how much time? O of n minus 1 time. Because the size of this is now one less. Here, are you following? So this is 6, this is, and then 0.4, and then just do a blank now. Again, so, and how many times we are going to do this? We are going to do n minus 1 times. Right? Or in some sense, till we have a constant. So basically the running time will be O of n plus O of n minus 1 plus like this. So this will run to n squared time. Is this clear? So this running time of this process, this is known as hop. This is the naive implementation. Just a straightforward implementation will give you offense, right? I can improve this one as well. Right? So each time I'm checking what's the minimum and the second minimum. If I can arrange these datas in such a way that the finding minimum and the second minimum can be done in much faster way, then I can improve the running time. So it's not that I always have to spend O of n time for finding minimum and second minimum. If I arrange the data in a nice way, I can find this minimum and second minimum in much better way. Right? Okay. So the thing is, using some data structure that we'll learn later, is can be implemented in O of n log n time. Right. So the using some data structure. So I'll name it using mean heap. There's something called heap, and we'll learn about this mean heaps as well. Using this mean heap, we can improve this in n log n time. Right. Actually, mean heap helps you in finding the minimum as well as the second minimum. You can also do in log n time. That the same process you have to do n minus 1 times. So that's why it turns out to be n log n. Right? And also I'd like to mention that in some special case, I'll say we can do it in O of n time. In fact, the I without using heap, I can also improve it in n log n time as well. And what are the special cases? Special cases are uh, the cases where we can linear sorting can be used. I'll maintain. So whatever I was saying here, let's say these frequencies are given in this array. First, I'll sort this array, sorting in the increasing order. Right? I'll sort them. That will make the minimum and second minimum will appear at the very beginning, right? And then I'll merge these two. Okay. And then it will end up at some point. Again, I have to insert that particular element in a proper place. Right. That I have to do. It's implementationally, it will be a little tricky, but we can improve this running time from n squared. Right? So whenever if someone asks what's the running time of Hoffman coding, its naive implementation is n squared, but I can do it in much better way, n log n. You should always come up with n log n. Its running time is n log n. Okay, fine. So any question about this? Okay. Okay, fine. So if there is no question, then yes, yes, I forgot to upload the last. So just after this class, I'll upload this lectures. Okay, fine. Okay, thank you, everyone.